Oh, you are correct. I'm sorry. Okay, David, I think we're live.
Okay, and I should probably stop sharing screen for just a minute. Maybe not. Maybe I should go back to sharing. This is, it's a high wire act. Sorry about that. So welcome to the presentation. This is getting the most from OpenRocket. I appreciate that you've come to join us. Allow me to introduce my colleague, Joe Pfeiffer. And there he is. Joe, you want to introduce yourself a little bit?
Well, hi, I'm Joe Pfeiffer. I am the secretary of the Fellowship of Las Cruces Area Rocketry Enthusiasts. So that's Flare number 577, and also Tripoli Las Cruces. That's Tripoli 102. I've been an OpenRocket contributor since 2018. Like a lot of people in rocketry my age, I got into rockets as a little kid. I actually still have the launch controller and launch pad my father built for me in about 1970. I outgrew it. Then when I had kids, got them into it. They outgrew it. I didn't. So here we are.
And I'm David Kane. I am the 2024 Secretary and at-large board member for SOAR and AR Section 571. I've been an OpenRocket helper since 2020. I don't actually develop the code, but I answer questions, try and help with communication, and do things like this presentation. You can reach me on Discord at JDDJ in the OpenRocket server.
And to interrupt, do we need to restart the sharing?
How are we doing now?
It's green now.
Okay, and folks, can you, I think you can see our slides. And I am assuming you can hear us. All right, so let's move ahead. Here's our agenda.
Yeah, what we're planning to do today is talk about how to, well, the title is self-explanatory, how to get the most out of the program. What we're going to do is we're going to start with some highlights from the current version, version 23.09. We're going to talk about interpreting simulation results. We get a lot of questions from users who don't really understand what they're seeing when they see the results, and especially when something unexpected happens, trying to figure out what's happening in the simulation causing that. We're going to look at a little bit more, let's say, advanced topic in component analysis and optimization, where how can you get OpenRocket to show you in a little bit of detail what's going on in the design itself. Then David's going to take over and talk about some of the file import-export features we have and using OpenRocket for 3D printing and the OpenRocket Photo Studio. So let's go on and talk about some highlights.
I think we might have lost our slides for a moment. Hang on just a moment and we'll see if we can get them back. Well, you're seeing our picture and our slides, says Todd. Okay.
Well, he was. I'm going to go ahead and just keep talking while David tries to get the slides themselves up again. Some of the highlights, we have some new features, which are we're pretty excited about. First off, we have some 3D printing support. It is now possible to export files for use with a 3D printer. We are now able to import and export RAS-Aero files. And this is very cool because you can design your rocket in OpenRocket and then get your aerodynamic calculations out of RAS-Aero. And RAS-Aero, of course, is known for having more accurate supersonic calculations than any of the other simulation programs. We have a dark mode user interface. A lot of users have been requesting that, and we're very happy to provide it. We're able to export there it is. We're able to export the simulation summary table to a CSV file now, so that you can look at it in the spreadsheet program of your choice and have it more easily available to you when you're not running OpenRocket. A couple of bug fixes. First, when I rewrote the tube fin drag code, I screwed up, and it only worked for the special case of touching fins all the way around touching tubes all the way around the body tube. And that's working much better now for some of the other use cases. And then finally, the base drag when using drag coefficient override is fixed now. Let's see, going next. Before we ever even start talking about our real topics, I want to mention, while people are still awake, some resources that are available to you. First off, something that's also new with this version that we're very happy about is we've got a series of tutorials that have been written and are being written by some of the developers, going through, actually, in some cases, some of the same topics that we are going through today. Also, if you go to our website, there's a whole section of documentation. And this covers everything from some people are and some people are not seeing the slides. That is interesting. We're gonna keep going and hope that you see the slides most of the time. The documentation has everything from how to do simple tasks to how to do things like drive OpenRocket from Python, all the way to Sampo's original master's thesis on the project. Also, we have a series of example rockets that you can get at from the program itself. We have a lot of people who ask, how do we get started? And starting with an existing example is a good place. We also have quite a bit of community support. And first off, we have a Discord server now, and you will find us hanging out on Discord just about all the time, and you can find it through this incomprehensible link. We also tend to be on Rocketry Forum a lot, and the advantage of Rocketry Forum is, first off, you don't need to trace down incomprehensible links. But if on Rocketry Forum you search for Discord OpenRocket, you will find a link to our Discord server. We're also on Facebook. A guy named Rob Goring has set up an OpenRocket channel on Facebook, OpenRocket page on Facebook, which is very active. And once again, incomprehensible, but in the case of Facebook, you can go to Facebook and search for OpenRocket, and you'll find that group. Okay, to continue. I'm going to talk about how to interpret your simulation results, useful plot variables. One thing that's a little awkward for people is you can set an x-axis that isn't time. And I want to talk a little bit about why you do that and what that looks like. And then interpretation of warnings and exceptions. And yeah, once again, unexpected results. Okay, to do this, I want to see if I can share my screen. And I think you have to unshare yours first, David.
Okay. Done?
Okay. Yeah, and I am trying to get there. I want to share entire screen. And with any luck, there's OpenRocket. Excellent. Okay, so I'm going to do this using one of our examples. It's our simplest example, the simple model rocket example. So there's the example. If I run a simulation, and this is a fully built, fully configured simulation. If I run a flight simulation, you'll notice that these little blue icons, what those mean is that this is a simulation that was loaded from the file. You notice this one is turned green. That means it's the results of a live simulation from this session. We go over there and we tell it we want to plot the results. And what it comes up with as a default is what is most useful for most users. The x-axis is time. The y-axis is the main things you need for performance: the altitude, the vertical velocity, and vertical acceleration. Let's go there first. And what the plot does is it tells you a story. It tells you what the rocket did in the course of its flight. And what it tells you is you had your motor ignition here at time 0. It took off. You can see what the acceleration did as a result of the motor. You can see the altitude. You can see where the apogee was. You can see recovery device deployment. And what you can see with this deployment, by the way, is that it's almost at apogee, a little bit late, but that's about as good as you're going to get with motor deployment. Let's take a look at a more unexpected result this time. And to do this, I'm going to take my rocket, and I'm going to take the fins off of it. Okay, let's see how it flies now. I'll run the simulation. A couple things to notice. First thing to notice is it got nowhere near as high as you would expect. Second thing to notice is over here, there is an almost invisible red exclamation point. And that exclamation point is telling you that something went wrong. And in fact, if you hover over this line, it tells you that there was a large angle of attack encountered 180 degrees, which means it was flying backwards. If we take a plot now, if we just take the same plot we did before, we see very odd things happening. We see our vertical velocity goes up for a ways and goes down. Apogee starts tumbling at apogee. We get a better idea of what went wrong if instead of that, we take a look at our stability against time. And stability is way negative. Okay, so we got that result because we flew an unstable rocket. Something else to show is what happens if things are so bad a simulation can't continue. And we have had people file bug reports on these things. So I'm going to go back to the rocket design, and this time I'm going to take the nose cone away. Okay, what's going to be important here is that the body tube makes almost no contribution to stability at all. And so far as OpenRocket is concerned, it can't calculate the stability. It cannot calculate the center of pressure. If you look up here, it's even saying stability, not applicable. Center of pressure, not applicable. If we simulate it, boom, error occurred, can't calculate stability, and it stopped at that point. Okay, so that's an example. That's a pretty extreme example of a really bad rocket. Let's see, where were we? Talked about these things. And I should mention that there are two kinds of exceptions like that occur. You have the exception, the simulation fault I just showed you, and then yes, you can get an actual uncaught exception. Those we want to hear about because those mean something happened that actually crashed the program. Okay. Another point is you can watch things occurring with an x-axis other than time. And let me do that. I can set. Oh, okay. Let's go back and have a reasonable rocket again, and run a simulation, and we can plot it using another x-axis, like for example, altitude, showing what's going to happen with stability as a function of altitude. We plot it now, and actually what's going to be better here is, David, let's go back to your screen, because there's a slide that shows how to interpret the changed x-axis type.
Okay, should be
Yeah.
there now. Almost.
Yeah.
Yep.
Okay, so once again, it tells a story. And this is a slide showing position east of the launch. And it's saying, okay, we start at this location 0. As we fly, the time is going up this line. It's saying we are going up here with altitude. So we're going to the right as we go up. And then as we come down under parachute, we come back to the left. And so that's an example of using plotting by something other than time. Okay. So, when we have unexpected, actually, this is a good thing to bring up again, just to be sure. One thing to mention that I've failed to mention before is that in the lower right-hand corner of your design window, it will bring up any warnings it can spot before you even fly the rocket. And it can spot, I can't quite read this slide right now, but I believe it's probably saying something about the fact that the front of your body tube is open. Okay. And yeah, we are trying to improve the warning system. Simulation aborts are actually already a lot better than you're seeing here for the next version. And we're trying to figure out how to make the warnings themselves better as well. Okay, so just to summarize unexpected simulation results, first, check your stability. I think we get more, why did this fly funny, from unstable rockets than everything else put together. Second place is people who fly a C6O and don't understand why the rocket stopped going up the moment the motor burned out. Something that I think we've got pretty much fixed is we would have people ask, how come my rocket came in ballistic even though it deployed its parachute? And what that normally turned out to be was 0 atmospheric pressure. So, and in general, follow that story that the plot tells you to verify your assumptions about what you think the rocket's going to do in that flight. And we have all seen this before. If this stuff is wrong, then your garbage in is garbage out. Okay, moving on a bit, I want to talk about component analysis. And I'm going to use, let's see, I need to go back to sharing. So, David, yeah, okay, you got your, darn it. Share screen, a window. I'm seeing what looks like, okay, I'm in the right place. Up here in the tools, one of them is component analysis. What this tries to do is give you an idea of how all the components of your rocket, let me try this again, because I seem to be sharing a window and not my entire screen. Window. That is certainly not it. Give me just a second, guys. I apologize for this. I promise it worked in rehearsal.
The squirrel's gotten tired.
That must be it. Oh, and this was a PebCam error. Sorry about that. Okay, so tools. We can look at component analysis. Component analysis will let us analyze stability factors, drag characteristics, and roll dynamics. Stability factors are typically the most interesting, I think. It tells us how each component affects the stability of the rocket. It shows the mass for each instance. And when you've got pods, it shows the aggregate mass, or as I instance mass, aggregate center of gravity, and center of pressure. Something I guess that can be surprising is trapezoidal fin set is not regarded as 3 fins. It's regarded as 1 fin set. The idea here is if you're using pods, it will, if I had 3 pods showing, then the aggregate mass would be triple of the instance mass. Now, the next interesting thing is drag characteristics. I'm going to tell you before I even open this that it has got some issues that I will tell you about as we proceed. Okay, drag characteristics tries to tell you how all the different components of the rocket affect the drag, the aerodynamic drag. Now, we have a model of drag that talks about pressure drag, which is drag that comes from the air hitting the front of the rocket, base drag, which is the vacuum behind the rocket, and friction drag, which is from the air flowing over the skin of the rocket. The idea is we look at a component and it says, what is its pressure drag? What is its base drag? What is its friction drag? What is its total drag? Then we also vertically add up all the components, get pressure drag, base drag, friction drag, total drag. And it shows both the drag per component and also what percentage of the total that is. Okay, now the problems with it. First off, the percentages are simply wrong. That is a bug, and that has actually been corrected for the next release already. Another issue is that the trapezoidal fin set, instead of giving you the pressure drag or friction drag for the whole fin set, it gives it for 1 fin. And so that's why these numbers are not adding up. If you take 0.024, because you've got 3 fins, they add up a lot better. And we get a certain number of people who would like us in the stability for that to also be per fin. I think that because of the way you manipulate the fin set, doing it per fin set makes more sense. Whichever side you are on that debate, doing it per fin set for stability and per fin for drag is wrong. Another issue that actually comes from how things are calculated elsewhere that I was just looking at yesterday actually is the calculation of pressure drag and base drag. And what happens is in the case of what OpenRocket regards as a symmetrical component, so like a nose cone or a body tube, it calculates the pressure drag and the base drag and reports them separately. So you notice the nose cone has a little bit of pressure drag, no base drag. The body tube has no pressure drag, quite a bit of base drag. For components other than symmetrical components, instead of adding them up separately, it computes the base drag and the pressure drag, adds them together, and reports it as pressure drag. So the pressure drag you're seeing here for the trapezoidal fin set is really the sum of pressure drag and base drag. And this is something we need to do something about. But that is the reason why a fin set will never show a base drag other than 0. Last thing that can be mentioned is roll dynamics, which if you've got canted fins or something, this will tell you something about how those are affecting it. Hand in hand with component analysis is we can actually have the program try to optimize your design a little bit. And what we can do say is, well, let's take a look at the fins. And do we need the fins to be this big? And could we fly a little better if we change their characteristics? You'll notice over here that there is a component tree that looks a lot like the component tree in the design window, except if we open up a component like the trapezoidal fin set, it will let us pick a parameter and add that parameter to the parameters to be optimized. And we can tell it we want to optimize for altitude, for example. We can tell it to start, and it will go through and redesign the fin. And the only thing it changed was what I let it change, the tip cord, to get a higher performance. Somebody is going to ask, how come I specified a minimum stability of 1 caliber, and let's see, and if I now apply this optimization, and having done that, it actually behaved this time. Sometimes we have seen stability here less than the minimum stability called for here. And I was going to tell you I don't know why that was happening, but I don't have to explain it away after all today. Okay, where are we? I think that this is a good time to turn it over to David to talk about the some of the other features.
Okay.
So let me stop sharing my screen.
There we go. And here we are. Okay, so I'd like to talk to you a little bit about some of the new file import and export features. The import and export features that are new live in the File menu. So I'll start with the design report. It's a really nice report that gives you sort of a wireframe picture of your rocket, outputs simulation info for motors, parts list, fin marking guide, cut guides, all kind of stuff. It is really nice. It allows you to select the data to print. You can print or save it as a PDF. I recommend you play with it a little bit, see what you like in there, and give it a shot. Next is the RockSim import export feature. This is also found in the File menu. If you're importing a file, choose File Open or File Import. Or if you're exporting to RockSim file type, choose File Export As and .rkt. The first thing to understand about this is that different capabilities between RockSim and OpenRocket mean that there's never a perfect one-to-one correspondence between the parts that go in and out. One good example is that OpenRocket doesn't do ring-tailed rockets yet. And on import, you're going to find that some of your RockSim components have mass and CG overrides. It's a minor annoyance, not a big one. Overall, OpenRocket does a great job of bringing in this foreign file format and if you've got to spend a few minutes adjusting things, that's sort of the price of doing something that's kind of a high wire act and pretty cool. It allows you to communicate back and forth with perhaps people that have RockSim and not OpenRocket. So they should all try out OpenRocket. Anyway, let me move on to RAS Arrow export. You're most often going to be doing file export from OpenRocket. It'll be on the file menu, choose export as and CDX1. The idea here is RAS Arrow is an aerodynamic simulation program more than a rocket pseudo CAD program. OpenRocket is a better choice for choosing the parts and building, assembling a rocket and simulating. RAS Arrow is reputed to be a little more accurate than OpenRocket over Mach. So if you're going to go supersonic, you may want to build your rocket into OpenRocket and export the data to RAS Arrow to then do some supersonic simulations. Importing from RAS Arrow is less likely, but it is also on the File Open or File Import menus. Finally, in the import and export, there's CSV. So you can export the simulation table to a CSV file to bring into your favorite spreadsheet or other application for massaging as you'd like. It's pretty simple. Just go into File, Export Simulation Table as CSV file. There are a few settings in there. They're not complicated. And go ahead and save. Next, let's have a look at a marquee feature of OpenRocket 2309, 3D printing from OpenRocket. This may be why a lot of you folks are here. So I'm going to give the short story because a number of Rocketeers are already 3D printing. So let's get the quick stuff out of the way. Here's how you do it if you know what you're doing, you think. You're going to find Wavefront OBJ export from the file Export As menu item, or you click on an object to select it, and in the context menu for that object, so that's a right click, you go down to the context menu, and at the bottom you'll see Export As OBJ. Once you've selected that menu, or that menu option, you will get the Wavefront OBJ export window. So again, the short version on this for people who are already doing this kind of stuff, you're going to pick a name for your exported object. If you don't name it .obj, OpenRocket will do that for you. Choose Customize for 3D printing, and you'll have to decide whether you want to export children. A case where you don't want to export a child is typically a nose cone. You don't want to 3D print a screw eye that you'd rather have as metal. So if the nose cone has a screw eye as a child part, just don't export it and just export the nose cone on its own. If you want a part and all of its sub-assemblies, and the poster child for this is a fin can, fins, motor mount, centering rings, you'll pick the parent part, which is probably a little piece of body tube, and say children, and all the things that are attached to that tube get moved into the mesh that you're going to export. There's a setting called Remove Origin Offset, and what that does for you, if you imagine you've assembled a rocket and there's stuff at the back of the rocket and there's stuff at the front of the rocket, removing Origin Offset puts everything at 0, 0, 0 for export. Decide whether it matters to you. In some cases, it just won't matter at all. And there's a lot more detail for the people who are doing quick starts at openrocket.info in the tutorials. There's a 3D printing export tutorial. So there are folks who are not 3D printing yet, and let's have a quick look at how stuff gets 3D printed. The first thing that you're going to need is to make or download or have a 3D printable object. So you might choose OpenRocket, or you might create something in a CAD program like Autodesk Fusion 360 or Tinkercad or FreeCAD. Or you may just have a 3D printable object that you're curious. Let me see how this prints. You get your first printer day one. Or you might want to download objects. You could get things from places like Thingiverse or printables.com. And it's going to come down in a mesh or wireframe file, the file format that OpenRocket is using. I'm sorry? I'm sorry. So the format that OpenRocket uses is .obj, and it's these mesh files. If you remember, like, or have seen a 1980s movie, they want to make things look futuristic. They'll turn whatever it is into a big mesh of triangles, and it looks like it's all computery. It'll look like that in the year 2000. So that's the kind of mesh file that is being created here. And common file formats are STL, OBJ, PLY, 3MF, and they have different kinds of data that they enclose in that file, but they're all doing sort of the same thing for our purposes. You're then going to take that mesh and you're going to have to slice it into layers, because your 3D printer is not printing triangles, it's printing layers of plastic and building them up. So you take it into a slicer, and the little picture here shows a slicer called Cura. It's very popular and it's free, works on Mac, PC, and Linux. You might also try Prusa Slicer, or Slicer with a 3 for the last E, or the only E, I guess, or Simplify 3D, which is a commercial product. These are a lot of good slicers, and there are a few other ones out there that you could investigate. And once you've got your sliced file, that's going to be called G code, and it's really machine instructions on how to tell the printer how to print. You're going to have to get that G code into your printer, and there are a few ways to do it. The way that I typically do is I hand it off to a 3D print server called Octoprint. I'll be happy to talk for an hour about how awesome Octoprint is, but not in this talk. If you want to hit me up offline, we'll chat about Octoprint all day, all night. Another way to get your G-code file into the printer is hook a USB cable to your computer and send it with your slicing program. That's going to keep your computer busy all the time that the print is happening. And yet another way to do it is to send your G-code to an SD card, plug the SD card into your printer. Things advance all the time in 3D printing, and there are probably some other options, Wi-Fi, and no telling what. But these are the common ones that I've seen a lot of. Next section, we include in the OpenRocket examples a printable nose cone and fins. And I want to go through how you actually get that going. This might be your first OpenRocket project because you've got something that you know will print. It's even included in the examples. So you find it in examples, 3D printable nose cone and fins. It looks very similar to a simple model rocket. And you're going to export the printable nose cone without children. You're going to export the printable fin can and motor mount with children, but make sure you do not have a motor configured. Otherwise, you're going to 3D print a motor into the hole in the motor mount, and you're not going to be able to get a real motor in there. No motor configuration when you export for 3D printing. Once you have exported that, let's talk about positioning the parts. You'll take it into your slicer. The slicer will help you position. Orient the fin can nose down. That keeps the motor mount hole completely free of support. It prints a nice clean tube that you can get a motor into and out of. The settings that I used, and this is a matter of individual machine setups, and it's kind of an art form, but what I used was I printed the fin can. You can do with or without support, and we'll talk about that more in a minute. I chose 20% infill and a 30 millimeter 3-layer brim. And I print the nose cone without support, 20% infill, 12 millimeter 3-layer brim. If you want to talk more about this in the Q&A, feel free to ask us. And I suggest that you print what makes sense. Don't print the body tube. Use a section of BT50. If you want to know more about why you might want to use a section of body tube, again, hit me up in the Q&A and I can detail it. I recommend that you choose a heat-resistant filament. I used PETG, which is shown here, and you can try ABS or ASA as well. I don't recommend PLA for printing this project. It just doesn't have the kind of heat tolerance that you'd want in a motor mount tube. Okay, I mentioned we talked about whether you want to print with support. I've got two examples showing here. Support gives you a little bit cleaner print, but it's going to take more material and longer print time. This fin can and fins was set up so you could print it potentially without support. If you print with support, like I said, a little bit cleaner. If you print without, you're going to have kind of a mess on the forward side of your engine block, motor block, and the forward side of the launch lug. But that's stuff that you can just clean up with a hobby knife. Real easy to do, and it'll save you maybe an hour, hour and a half of print, depending. So let's talk briefly about designing for 3D printing with OpenRocket. I'm going to suggest that you avoid excess geometry. There's no reason really to make centering rings. The only reason they're in the example is because it was adapted from a model that had centering rings. You can just make the motor mount tube have walls thick enough to reach the inside diameter of the body tube, and all of that space in between will just get filled with the printer's infill, which could be 20%, 15% infill. You don't have to make it more complicated. It'll take longer to put all the little walls and voids and stuff in there if you make centering rings. Don't make extra voids, sort of referred to that a second ago. So empty spots that the printer is going to have to make walls around makes for a more complicated slice, longer print, and doesn't really get you anything. Your minimum feature thickness is going to be at least one nozzle width, and most hobby printers, at least when I've started, have started with a 0.4 millimeter nozzle. You may have something else, so figure out what it is when you're designing. Decide what goes together. We talked about a fin can. The fins and the stuff in the fin can, yeah, they go together most likely. What prints separately? 3D prints have a weak axis, and if you need to cater to that weak axis, so for example, you've got stacked up weak axes, you might want your all thread for an AV-based sled to go through those weak axes to strengthen them up a bit, but you might want to print the sled for your bed laying down on the print surface, just because it makes more sense to print it flat. So you'll have to think about these things as you design, and it's kind of an art form. You want to think about how you're going to interface with metal and other components. OpenRocket doesn't offer you tools for drilling a special hole someplace. And so mounting and vent holes are probably not something you're going to be able to do in OpenRocket. You'll have to drill them. And if you need to adhere things, figure out whether you've got a compatible adhesive or whether you can make a mechanical bond. If you're doing epoxy a lot, you probably understand how mechanical bonds are important. Last thing, consider when it might make sense to use a tool other than OpenRocket. OpenRocket exports a wireframe-like mesh, and that prints great, but it's hard to edit a mesh. Most of the tools are not designed for mesh editing. They're designed for CAD-type editing. A procedural modeler like Fusion 360 or Tinkercad or a parametric like FreeCAD, all of these are designed for CAD work, and it might be better for things like doing mounting holes or screw threads or heat set inserts, any of those things. OpenRocket just doesn't do that. So I'd suggest to you check out Scott Miller's vNarcon presentation on 3D printing from earlier today. The recording should be available to you. And Chris Taylor's 23 and 24 presentations on 3D printing. Chris is really talented. And of course, the OpenRocket 3D printing tutorials on openrocket.info. We're going to move on to talk about the photo studio next. If you have a look at these images, wouldn't any manufacturer love to have a picture like this of their rocket kit on the outside of their packaging? These nice models were created by Neil Weinstock. He's really talented, and they are just lovely. I can't really take any credit here. I just used the stuff I had at my disposal to create these images, and I did it with the OpenRocket Photo Studio. I didn't even know that OpenRocket had a photo studio until I went to help with some of the documentation. To get at the photo studio, it's in the tools menu, photo studio, and you can control everything you need to make a great image. So rather than talk you to death, let's go through a demo of some photo studio stuff. This is a model of an Estes Argent Pro Series 2, one of my faves. And I'm going to find the photo studio up here on the tools menu, and I'll bring up the picture. So you've got a settings tablet with 3 tabs. And when you're done, you're going to go to the file menu to save your image. Okay. So let me start out here actually with just a standard background. Okay. You've got a color background. You've got pitch, yaw, and roll controls to position your model, like so. That's sort of standard rocketry and aviation type control. And you've got advanced, which says how far through the frame is the rocket going to be going. You've likewise got controls for the camera, and they're different things. The camera can wander around the model, and you can go up and down with the camera altitude control. You can change your view distance from the model. This is like, there's a distinction here in view distance. This is like walking to and walking away from the model. Your perspective of the model will change because your distance from the model changes. Then there's field of view. The model gets bigger or smaller, but it's like zooming a zoom lens. Your perspective doesn't change at all. It just gets bigger and smaller in the frame. Okay. There is some positioning that you can do by dragging your cursor around in the window. But I want to point out what you're doing is you're positioning the camera, not positioning the model. When we get into backgrounds in a moment, we'll see that the background moves with the model when you are positioning this way. And there's nothing wrong with that, but you ought to know what you're doing, what you're positioning, so you have the easiest time getting the results that you like. So I'm going to change the environment up a little bit. We had the mountains image, I think, up when we came in here. And so here again, you're moving the camera around the rocket when you're dragging, and you see the background move in relation to the rocket as we do it. So you can control lighting color. You can control ambience, which says how much ambient light is there. If the light is all the way on, there are no shadows on the rocket at all. All the way off, you get very dark shadows. I don't recommend having no ambient light. You need some shadow fill to make the image look normal. And you can control the azimuth and altitude of the light as well. If you want to light and shine up your rocket really nice, these are the controls that can help you do that. So you might say, I want to see that line of shine that goes down the rocket. We have a number of nice backgrounds here. Here's meadow. And I think most of these are 360 degree backgrounds. Stormy days and frozen lake. Those guys have got to be cold. Orbit, sort of space looking. And Miramar, sort of clouds. I'm going to go back to Stormy Days because Stormy Days is almost sunset in color. And when we look at the rocket is lit with a pretty, noonday white light. So what I'm going to do is I'm going to adjust the sunlight color. And I'll pick something that's kind of an orangey thing. Now that's a lot. That's extreme. That doesn't look real, right? Well, what you can do is you can go into the hue saturation value or hue saturation lightness and just choose how much saturation you want from, it's a white light to just warming up that color a little bit. You can go to too much if too much is what you'd like. Anyway, so that is that. Another thing that I want to point out that you might really like is that there's some effects available in the photo studio. You can have smoke and flame and sparks. And you can see I've turned them all on. There's no smoke, there's no flame, there's no sparks. What's going on here? Well, there's no motor in the rocket, and you have to have the rocket configured with a motor if you want to see smoke and flames and sparks. So let's go back to our photo studio. And now we've got smoke and flames and sparks now that I put a motor into it. So I'm going to adjust the orientation of my model a little bit. And I will turn off some of the effects so you can see them one at a time. Let's see. No sparks without a flame, apparently. That's a new one on me. So there is flame. and there's some smoke, and you can change the opacity of the smoke. You can change aspect ratio of the flame to get something that looks the way you want it to. Um, if you've got flame, you can apparently have sparks, more or less sparks. You can change the flame color as well. Spark weight. So I guess that's more, more or less uh, length to the sparks. And finally, there's speed. I have not found speed the effect to do much of anything. I'll tell you one more trick, and then we're out of Photo Studio entirely. You've got this nice blue background here. If you wanted, you could make the sky color completely transparent and export the image. Once you've done that, what does that what does that let you do? And I will show you right now. You can export an image on a transparent background, and that lets you drop it into another image of your own choosing. Uh, Pretty cool. If you've got a photo editing program and some skill with it, you can move this around all kinds of different ways. I'm going to turn this back to our slide presentation, and I'm going to hand it back to Joe.
Thank you. Um, there we go. Looking ahead, uh, we've got a bunch of stuff that we are looking at doing going forward. Uh, we One thing that's important, I think, is to improve our supersonic flight simulations. Lots of people want us to be able to have rounded nose cone tips. Something I really want to see happen is to be able to export a KMZ file so it can be imported into Google Earth, and we can have a track of the flight, overlaid on the launch site. Um, this has safety enhancements, and they are safety enhancements, but just in general, more and better warnings. We don't tell you when you're too slow off the launch pad, too slow off the rail, and we also don't tell you when there's a high angle of attack, because as you come off the launch rail, there's a high crosswind. Um, fin flutter is a very important topic when you get up around supersonic, and we really ought to be calculating that. We have all the data for it. Ring fins I want to see. And okay, I could list all this, and basically we've got a lot of stuff we want to keep doing, and we need help to do it, please. Let's see. Yeah, and we can go on to how you can help. Yeah. First off, all of our users are testers. This is true for any software. If something happens that you don't understand, and especially if you get a crash, there is a mechanism within OpenRocket to report a bug, or hit us up on Discord or Rocketry Forum and ask what's going on, and we will either explain it or we will file a bug report. Or, of course, if you're on GitHub, you can file a bug report yourself. Documentation. I mentioned copious documentation way back at the beginning of the talk. A lot of it dates back to version 15.03, and it needs to be updated, and more stuff needs to be documented. Always looking for suggestions. Always looking for programmers. There's just a few of us that are hacking away on this, and there's lots of issues that you would be welcome to tear off and write some Java. Translations. We support 15 languages right now, and of course, we do not have developers who speak 15 languages, so a lot of those translations are getting more and more out of date, and somebody will be working in Arabic and suddenly have prompts. Some of the prompts turn up in English. If you speak, or you can read and write any of the languages that we support, or a language we don't support, we can help you get started with doing a translation. Okay. And I mentioned some of these locations earlier for where you can find us. Last thing is thank you to people. We have 50 code contributors going back to when the project first started. Well over a decade ago. There's only been a few at any given time. There aren't nearly enough right now, and we'd love to have some more. Special thanks to our 39 financial contributors so far. Trying to maintain the signing certificates for Macintosh and Windows costs money. We are healthy at the moment. We will be able to keep those going for some time to come, but we are very grateful to those of you who have made it possible. And download it from OpenRocket.info/downloads or fork it over on GitHub today. And thank you all very much. There have been some questions that have come in during the talk, and I think I've answered a couple of them over on that talk window, over on that Q&A window. Anybody else have any questions? Type quickly because I think we're just about out of time.
I think SIBO may have answered the laser cutter question. We'd like to get SVG export working. Any other questions for us? Feel free to ask.
And I am looking at my clock, and I think we are actually out of time. So I'd just like to thank you all for attending and listening in on this.
Thanks, y'all.
Thank you, David.